In this video, we're going to explore the rules around differentiation. To start with, we'll explore what the derivative actually is and what it tells us about a function. We will then cover the table of known derivatives, as well as some of the key properties of the derivative. And finally, we'll cover the 3 techniques that you'll need to know for the exam. Let's get into it. It is often important to know the rate of change, or gradient, of a function. And the derivative is one technique that we can use to find that gradient. Up until now, if you wanted to know the gradient of a function at a specific point, then you would have to use the IROC equation. But that's quite a lengthy process, and we wouldn't want to do that for every single point along the function. The derivative is one method in which we can shortcut this. The derivative of a function tells us the rate of change of that function for any value of x. For now, just take it at face value that the derivative of x squared is 2x. That derivative itself is a function, and like any other function, it has a graph. The graph of the derivative function makes it easier for us to visualize the gradient of the original function. For example, if the graph of the derivative function is above the x-axis, positive y values, then the gradient must be positive. And if it's below the x-axis, where it has negative y values, then the gradient must therefore be negative. Okay, that's all well and good, but how do we actually find the derivative? That's where the table of known derivatives comes in. This is the table of known derivatives that you'll be expected to know for the exam. You won't have to technically memorize them as such, since they will appear on your formula sheet in both the tech active and the non-tech active exam. But because this is very core to the entire area of study of calculus, you'll end up memorizing them anyway. So here's how it works. On the left-hand side is the original function, and on the right-hand side is that function's derivative. For example, if you wanted to find the derivative of x squared, then you could refer to the table. X squared is a power function, and as such, it corresponds to the first entry of the table. We simply need to observe that n equals 2, since x squared has a power of 2. Now that we know that n equals 2, we simply sub in that value into the derivative equation, and thus obtain 2x as the derivative. There are a few ways to express the derivative. In this example, I've used d on dx notation, where you simply write d divided by dx before the function, and then encase that function in brackets. More commonly are these two expressions here. If your function uses function notation, then f-x is used, or f prime of x. If your function is simply expressed as y equals f of x, then dy on dx is used. All in all, you just need to make sure that you're using the same notation that the question is using, and this will typically be told to you in the exam. Okay, but what happens when we're trying to find the derivative of a more complicated function? Ultimately, all we're ever trying to do is rearrange the equation until we get a match on the table of known derivatives. And there's a few properties of the derivative that we can use to our advantage. Firstly, the derivative is considered a linear operator. All that means is that these two things are true. Firstly, if your function is multiplied by a constant, then you can distribute that constant outside of the derivative. And lastly, if you wanted to find the derivative of an addition or subtraction of two different functions, then you can instead find the derivative of the first function and add or subtract it from the derivative of the second function accordingly. Firstly, we can see that f of x is a subtraction of two different functions, so we can use the second property to evaluate the derivative of each term individually. Next, we can use the first property to distribute those coefficients outside of the derivative. From here, we can refer to the table of known derivatives to find the derivative of each term individually, and thus find the derivative of the entire function. Okay, well, we can handle addition and subtraction of two different functions, but what about multiplication? This is where the product rule comes in handy. First, we just need to define what those two functions are, u and v. It doesn't matter which one you give to u and which one you give to v, because the order can be swapped. It is a product of two terms, and it doesn't matter which order you write them in. Next, we need to find the derivative of both of those functions, which you can do using the table of known derivatives. Now that we have all the required terms, we can substitute into the product rule and then simplify the result. How about division? Well, in this case, we'll use the quotient rule. Just like before, we have to define what u and v are, but this time the order matters. U must always be the numerator, and v must always be the denominator. Don't forget, if you ever get stuck, you can always refer to the reference sheet in your exam. This is a very easy one to get back to from. So, as before, we're going to find what u is and what v is, as well as their derivatives. Once we have those, we'll just substitute into the quotient rule and simplify the result. So I've saved the hardest one for last. The chain rule helps us find the derivative of composite functions. I've left a link in the description if you want to review what composite functions are, but for the purposes of this discussion, you can think of composite functions as functions that are nested inside other functions. The chain rule itself is quite simple. If you want to find the derivative of a composite function, you first find the derivative of the inside function, g of x, and then multiply it by the derivative of the outside function, f of x. The hard part is finding out if you even have a composite function to start with. If you're ever unsure in the exam, here's a litmus test. If none of the other rules apply, then it must be the chain rule that applies. Let's go down the list. F of x can't be a product of functions because the x squared is inside the circular function, not on the outside. For that exact same reason, it can't be a division of functions either, so it must require the chain rule. F of x is a composite function. It has a function x squared inside another function, sine x. So we define g of x as x squared, since that's what's on the inside, and then f of g is going to be sine of g. Remember, we've defined g of x as x squared, so we're going to use g now instead of x squared. Now all we have to do is figure out the derivative of each of those terms. Just be mindful that you use the correct letters. We have dg on dx, which is the derivative of g with respect to x, and we have dy dg, which is the derivative of y with respect to g. Once you have both derivatives, you simply substitute into the chain rule. So you're going to multiply both of them together and then simplify the result. Just don't forget at the end to replace g with x squared, because we want to have everything in terms of x by the end of the equation. With differentiation, there isn't necessarily a one-size-fits-all approach. You may be able to use multiple rules for the same function. I'll demonstrate with an example. The chain rule can be used to find the derivative of this function if we define g of x as 2x plus 3. When we do that, it becomes a bit clearer that we can use the first entry of the table of known derivatives since we have something raised to a power. That something just happens to be a function, which is why we have to use the chain rule. And so after a bit of simplification, we end up with the derivative. Alternatively, you can rewrite f of x as a product of two terms, since it's just 2x plus 3 multiplied by 2x plus 3. And sure enough, you'll get the exact same result. And lastly, we could expand the brackets entirely and just solve the derivative of the entire polynomial one term at a time. And sure enough, get yet again the same answer. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll send you to my website.